Good morning. So we shall continue our discussion. Uh, so the next topic is, so we are entering into partial differential equation. So why this partial differential equation? So the mathematical formulation of many problems in science and engineering reduced to study first order partial derivative equations. So for instance, the study of first order PD arises in uh, the problems like gas problems, traffic flow problems, and motion of waves, etc. So therefore it is very essential to study the theory of first order PDs and nature of their solution to analyze the physical problems. So we shall see the definition of a partial differential equation, an nth order partial differential equation. So we shall begin by the definition. PD. So a partial differential equation So in short form it is PDE, partial differential equation. For a function u of say x1, x2, so on up to xm, where this m must be greater than or equal to 2. Independent variable, a function of independent variable xi, the function u and its partial derivatives like dou u by dou xi and dou square u by dou xi, dou xj, and so on. So a partial differential equation is a relation of the kind f of x1, x2, so on up to xm, and u, and partial derivatives of u with respect to the independent variable xi to 0. So let's call this as equation 1. So where the finite number of derivatives, in this there are only finite number of derivatives occurred, and f is a known function of independent variable xi, unknown function u, and partial derivatives of u. So f is defined on a domain omega of this x1, x2, so on up to xm, u, dou u by dou xi, dou square u by dou xi, dou xj, and so on, space, where this xi is u, dou u by dou, they exist. So together it's a space. So we say that the function u of x1, x2, so on up to xm defined on a region on a domain D of x1, x2, so on up to xm space is a solution of the partial differential equation 1. Is a solution of partial differential equation 1, that is this. So if u, and we say that this u is a solution of differential equation 1. If this u and its partial derivatives, if u and its partial derivatives that's appearing in this equation 1 exist and continuous in D. This function is a solution of 1 if u and its partial derivatives exist and continuous in the domain D. So as you've seen in ordinary differential equation, the order of a differential equation, so similarly the order of a partial differential equation, differential equation is the order of highest derivative present in the equation. So for example, if I take say dou u by dou x, dou u by dou y is equal to say u square, then the highest derivative term is this one or this one. So we can say this is a differential equation, partial PDE of order 1. It's a partial derivative differential equation of order 1. Similarly, if I take it as uxx plus x into uxy minus ux minus e power xy minus sin u equal to 0. Now, what is uxx? Uxx means it is dou square u by dou x square. And what is uxy? It is dou square u by dou x dou y. So we can know the highest derivative term is dou square u by dou x square or dou square u by dou x dou y. Therefore, the order of this partial differential equation is 2. So a partial differential, okay. So we shall see. So we have seen the general definition of partial differential equation. So we shall see simultaneously what is first order partial differential equation. This first order partial differential equation. So the general form we shall see here itself. So we shall general form of first order partial differential equation in two variables x comma y for the unknown function u is. So here in this we have seen the form of partial differential equation in m variable x1, x2, so on up to xm, and unknown function u and its partial derivatives. So here we are seeing the general form of first order partial differential equation in two variables x and y for unknown function u. So given that it's a partial differential equation, so f is a function of x, y, and u. Moreover, it contains first order derivative, so it is ux, uy, and it will not contain ux square or uxx or uxyy or uxy, because it's a first order. So general form of partial differential equation is f of x comma y comma u comma ux comma uy is equal to 0, or we are also denoting this by f of x comma y comma u comma p comma q is equal to 0, where p is nothing but ux and q is nothing but uy, and f is a known function. F is a known function. Similarly, the general form of second order PDE in two variable x comma y for the unknown function u, is given by, now, f of x comma y comma u, and it's the second order PDE, so it contains ux, uy, next uxx, uxy, uyy equal to 0, or this is equal to f of x comma y comma u comma p comma q comma r comma s comma t is equal to 0, where again p is nothing but ux, q is nothing but uy, r is nothing but uxx, s is nothing but uxy, t is nothing but uyy, and f is a known function. So there are some categories of a partial differential equation. There's a linear and non-linear. So a partial differential equation, again we shall say in general, a partial differential equation is called linear partial differential equation. If it is linear in u and its partial derivatives dou u by dou xi, dou square u by dou xi dou xj, and so on, with coefficients depending only on independent variables. So linear PDE, if it's linear in u and its partial derivatives with the coefficients depending only on independent variables. So let's take an example. So it is dou u by dou x plus dou u by dou y is equal to u square. Now it contains the terms dou u by dou x plus dou u by dou y. So dou u by dou x has a coefficient 1, so no problem. Dou u by dou y coefficient is 1, and it's a u square. But I can write this u as u into u. So u is a function and it has a coefficient as a dependent variable. This is like a dependent variable. So it is not a linear differential equation. So here we defined what is linear differential equation. So if it is not linear, then it is, otherwise it is non-linear. Therefore this equation is non-linear differential equation, non-linear partial differential equation. Then what's an example of a different on linear differential equation. So take x ux plus y uy equal to z. That is nothing but x into dou u by dou x plus y into dou u by dou y is equal to z. Now see, this depends on x. Dou u by dou x as a coefficient x. It's an independent variable. Dou u by dou y and coefficient is y. Again, it's an independent variable z. So no problem. So this is a linear differential equation. Linear partial differential equation. So we shall see. So now this is the definition of linear partial differential equation in general. So again, we shall see in what happens in first order PD. So the general form of first order. So general form of first order linear partial differential equation in x and y for the unknown function u. For the unknown function u is given by, now observe, it is a of x comma y into ux, that is coefficient depends only on independent variable x and y, plus of x comma y uy plus c of x comma y u, which is equal to d of x comma y. Here the coefficients depends only on independent variable. So what is the form in second order partial differential? So general form of second order linear PDE, linear partial differential equation in x and y for the unknown function u is a of x comma y ux x plus b of x comma y uxy plus c of x comma y uyy plus d of x comma y ux plus e of x comma y uy plus f of x comma y u, which is equal to say some c1 or e f g, g of x comma y. Now if you observe, all the coefficients depends only on the independent variable, therefore these are the linear partial differential equation. Okay. Let's move forward. So next is this non-linear PD is again classified as it is not equally classified. There are two sets of non-linear partial differential equation. So one is a partial semi-linear partial differential equation. That is a partial differential equation of order n, of nth order partial differential of order n is called semi-linear partial differential equation if it is linear in its partial derivatives of order n with their coefficients. If it is linear in its partial derivatives of order n with coefficients with their coefficients depending only on the independent variable. So the example is do u by dou x plus dou u by dou y, which is equal to u square. So it's a semi-linear partial differential equation. So we shall see in terms of first order. So in first order, yeah, we are considering first order PD into variable x and y for the function unknown function u is now a of x comma y ux plus b of x comma y uy is equal to c of x comma y comma u. So this depends only on independent variable, this depends on independent variable, this depends on x, y as well as the dependent variable y. Therefore it's a semi-linear. So the next one is a quasi-linear. So a partial differential equation of order n. So a partial differential equation of order n is called quasi-linear partial differential equation if it is linear in its partial term, if it is linear in its partial derivatives of order n with their coefficients depending on the independent variable xi and possibly on u and its partial derivatives of order less than n and its partial derivatives, that is partial derivatives of u of order less than n. So for example take uxx plus uyy plus u square equal to 0. Now observe the coefficient of uxx is nothing but ux, coefficient of uyy is nothing but again a derivative, partial derivative of u with respect to y. So this is the quasi-linear equation, quasi-linear partial differential equation. So again the general form of first order quasi-linear partial differential equation into variable x comma y for the unknown function u is a of x comma y comma u into ux plus b of x comma y comma u into uy is equal to c of x comma y comma u. Yes. Now let's see what is homogeneous, when we can say a partial differential equation is said to be homogeneous. So if it's each terms contain independent variable or its derivatives. So partial differential equation is said to be homogeneous if its each term contains the dependent variable or its derivative So an example is do u by dou x plus do u by dou y, which is equal to u square. Now each term contains a dependent variable or its partial derivatives, hence it is homogeneous. But if I consider it is ux uy plus y into u, which is equal to x. Now this contains a partial derivative of u, this contains u, but this does not contain the u or its partial derivatives, therefore it is not homogeneous. Not homogeneous. Okay, so next we shall see what are the okay we shall see in this next class. Thank you.